Welcome to NASA Explore School Web Chat. My name is Christy Hill from Marshall Space Flight Center. Today joining us we have Sam Ortega, a civil engineer here at Marshall. I'm going to let him introduce himself before we start the questions.
Well, like Christy said, I am a civil engineer, but that's just merely the degree that I received when I went to school at Texas A&M University. Actually, since being here at Marshall, I have been involved with structures, which we do with civil engineers, but my structures were more the things that flew inside the cargo bay of the space shuttle, as well as the space shuttle itself. I've also handled microgravity experiments, getting those ready, and to date, right now, I'm actually working on the solid rocket motors of the shuttle boosters for the space shuttle itself.
Okay. Well, the first question has come in, and the question is, what is it like to fly on the Weightless Wonder?
Well, the Weightless Wonder is the KC-135. It's an airplane that NASA has to fly parabolas. So basically we fly up and we fly down, we fly up, we fly down. And as you get to the top, everything floats. And so you'll float for about 40 seconds. Another name for it besides the Weightless Wonder is the vomit comet. So as you can imagine, when you get into microgravity environments, and more so when you're down at the bottom going down, everything weighs twice. So I normally weigh about 150 pounds, so I'd weigh 300 pounds down at the bottom. And the blood comes rushing out of your head, and it really does make you, or can make you quite dizzy. And so people tend to not feel so comfortable flying in the vomit comet. I was fortunate. I didn't have many problems with that. It's really a neat sensation. When we first went flying, I had quite a bit of bravado and had my experiment ready to work on. And I kept telling all my cohorts, not a problem, I'm going to do science on the first flight, first parabola. And everybody says, no, just do the ride, Sam. Learn how it goes. I kept saying, insistent that I was going to do science, and when the first parabola came, I proceeded to feel like I was tumbling over. I grabbed my experiment and I pulled as hard as I could to feel the pressure on my bottom as if I was still sitting on the floor of the airplane, and it didn't work. I got no science done at all. But it's a great experience. It was a lot of fun.
Great. Well, question number 2, is it difficult to work with space scientists that live in other countries?
No, not at all, because we all have the exact same goal. We're wanting to get their experiment to work in microgravity. The only difficulty was maybe language barriers, but we here at NASA would have them provide a translator, and so we'd be able to communicate. I did have an opportunity to work with Ukrainians for a space welding gun using electron beams that they're going to propose to use on the space station. I've had the ability to work with engineers from the Netherlands. I've worked with engineers from Italy for the tethered satellite system that we flew back in the 80s. So mostly I think everybody has the exact same goals in trying to get their experiments flown, and it's just the language part, but we work through that.
Okay. Well, question 3, what will you work with once the space shuttle has retired?
Actually, I've already started my transition. So
okay.
my new job coming out of Space Shuttle, once we do fly our last mission here sometime in the June timeframe potentially, is Centennial Challenges. And it's a program we've actually have been doing for a few years here at NASA. We're trying to expand it. And what we do is we offer prize money. We'll put up a challenge, an innovative challenge, and offer prize money to somebody who can achieve the goals for what we've put up for a challenge. For example, with it being called Centennial Challenges, it is named after the centennial of flight, the 100th flight anniversary of the Wright brothers. So what we're really trying to focus on is the people that were standing on the beach at Kitty Hawk when the Wright brothers first flew. They all stood there and realized an airplane flew and questioned each other, so what? Who cares? I've got my horse. And what kind of, it's not going to make a big difference, but yet here we are flying around the Earth now in the space shuttle airplane. So with our Centennial Challenge, we're trying to do the exact same thing. We'll have technologies offered. Some of the things that we've been doing are power beaming, which would be a space elevator. The technology concept being that you have something 22,000 miles outside the Earth in a geosynchronous orbit, but it's attached to the Earth with a tether. And then you have something that would be able to, a platform that would be able to climb up that tether to microgravity to be able to do experiments. Well, in order to do that, the power needs to be beamed wirelessly. So we're trying to transmit electricity in a wireless fashion and over long distances with large amounts. And so that technology we've actually been doing. We've had success. Teams have actually won a $1 million prize on that one.
Wow.
And so we're going forward with that and coming up with new technologies also to advance. We've got a project, or a challenge here in July, which is an electric airplane. And so we're trying to improve the efficiency of airplanes. For example, if you fly a little Cessna airplane for 200 miles, it might take 9 gallons of gas. Well, the challenge is to take an airplane and fly it 200 miles on 1 gallon of gas or less. So I'll be working with that here for the next few years probably.
That's great. All right, well, the next question is, what is a civil engineer and what do you do?
What is a civil engineer? The field of civil engineering covers a lot of areas. There's structural engineering, there's petroleum engineering, there's geology aspects of it, there's environmental engineering, and all those tend to fall into the field of civil engineering, along with roads and buildings and railroads, all of that aspects. My field that I studied was actually just structures and structural engineering. I took that into the space field. So everything is still the same. Loads, forces, stresses. It doesn't matter whether it's on Earth, whether it's on the moon, whether it's on Mars, whether it's in the space shuttle, the space station. The concepts are still the same. The math principles are still the same. The engineering principles are still the same. And so within the civil engineering, I just took advantage of the structural side, but I knew I wanted to work in aerospace, and so I took that tack to get here.
All right. Did you ever have a rocket that blew up while you were testing it?
No, which is a good thing. For the size of rockets that we have with the space shuttle, it is the world's largest solid rocket motor. It does produce around 3 million pounds of thrust with 1 million pounds of propellant. An explosion with that one would not be a good thing. That'd be a very difficult thing to have to go off and deal with and do the analysis on. Have I ever had a rocket explode on me? No, not even playing my little model rockets, the Estes rockets. I've been fortunately not to have to do anything with failures of that kind yet.
All right. How did you get interested in your job?
That would come from my brother. My oldest brother is in the Air Force. Was in the Air Force at the time, and he was launching satellites for payloads into orbit. And I was a junior at Texas A&M University at the time. I had just finished up a reinforced concrete design class and kind of realized I didn't want to do buildings and bridges for a living. So I called my brother up and kind of talked to him about what was going on, and he proceeded to inform me that, like I'd said earlier, space structures are the exact same as Earth structures. It doesn't really matter. So if you want to work aerospace, call somebody up, start working aerospace, and call me back when you have a real problem. So that was kind of the kick in the pants there for that one. So I went off and started working with figure out what I was going to do getting out of school, and happened to do a favor for somebody there at Texas A&M, and she happened to be the head of our co-op office. I went back to her about a year later and expressed my concerns with wanting to work in the fields of buildings and bridges, and she said, well, tell you what, let's get you into the space field. So called around and tried to find a job, and she had her people in the office looking at McDonnell Douglas and Boeing and different companies, and told me what I could do. So I went back and got the phone book there from Marshall Space Flight Center and found who was head of the structures department and called him up. It was a man by the name of Ron Jewell, and I distinctly remember when I first called him, he answered the phone with a pretty gruff voice, says, "Hello?" And I just kind of startled at first, and I went in and said, well, my name's Sam Ortega. I'm a student here at Texas A&M University. I'm looking for a co-op position. He goes, how'd you get my name and number? And so I kind of went through that discussion. I looked in the NASA phone book, and I found that you're head of the structures department. I apologize if it's inappropriate for me to call you, but I am looking for just a co-op position. And he goes, so you thought you could just call NASA and ask for a job, did you? And I said, well, not really, sir. But again, I'm just looking for a co-op position and some temporary positions. And he goes, well, that's a pretty good initiative. You're hired. So that's how I got my job with NASA, and came here and started co-oping, which is I worked for a semester, and I go back to school for a semester and work a semester until I graduated. And I guess I did okay because they did offer me a full-time job afterwards, and that's how I got to be working here for the very beginning.
That's great. All right. I have another question. How did you decide what kinds of challenges that you're going to offer with the Centennial Challenge, and who can participate?
The method of going off and finding our challenges, we sit down with people in the industry. We'll go to a lot of conferences throughout the country to different people that are working commercial space or just other technologies. And we also look inside of NASA. We talk to a lot of our engineers because we want to make sure that we're grabbing a technology that we have an advocate. We have somebody inside of NASA that wants to understand better what we need to go do or what they foresee in the future us needing, and going off and trying to explore that area a little bit more. So it's a group effort between industry and NASA ourselves. Once we find and narrow it down, we'll go off and find some more experts within NASA and industry and really kind of narrow down the exact details of what we want to do with this challenge. Every challenge is generally at the prize levels of $1 million to $2 million for the challenges themselves. And we really do try to focus it for citizen inventors. We want people that be innovative in their solutions. We don't want a large company that can throw millions of dollars to solve the problem and come back and win the $1 million. That's not really what we're looking for. We're looking for somebody in their garage or somebody in a little laboratory where they go off and they got a very innovative, inexpensive, easy solution to the problem. And that's what we want to try to expand on. So we'll have those types of citizen inventors working to go for the competition. One of our other outreach and tenets of our Centennial Challenges is that we'll go off and we have student-run competitions also associated with each challenge. So as each challenge comes up, they'll have involvement methods for high school and college level students to get engaged in the challenge. Sometimes there's prize money awarded and associated with the student level competitions as well as with the main prize level itself. But if there's people have interest in trying to find out how they can participate within the challenges, you just have to go to www.nasa.gov/challenges, and then all of our challenges are listed there.
Okay, great. If you do not see your name in the chat box side, hit your refresh and then type your name back in so that you can see your name in the chat panel. And we'll go on to our next question. What does a solid rocket motor mean?
A solid rocket motor is a propulsion device. It's a propulsion method where you'll take different types of chemical components, you mix them up, and it's really kind of neat. We have for the solid rocket motors we use in the space shuttle, they're manufactured by Alliant Tech Systems out near Salt Lake City, Utah, up north of the Great Salt Lake. They bought some originally 500-gallon big bowl bread mixers, the industrial bread mixers, and that's what we mix the propellant in. And so you mix it up, and it has, when it first comes out, it's kind of a peanut butter consistency. It's really kind of a thick, creamy stuff. You'll cast it inside of a metal cylinder and have a shape or a form that allow you to have different types of levels of performance of your motors, whether you're going to have high thrust at the beginning, high thrust at the end, or however you want to do that. And then you put it into a cure cycle where you might get a temperature a little bit higher and just let it sit so it'll bake essentially and cure and harden up to where it's about the hardness of a pencil eraser. After that, it's a live propellant. All you need to do is either light it off with some sort of a flame or an igniter, and that'll get the whole thing up and burning.
Okay. How many rockets have you built?
Well, I've been with the shuttle program now for about 8 years. We've probably done 20 or 30 some odd flights and 2 per flight. So I've been working with the construction of probably 60 different motors that have been flown on the space shuttle. Personally myself, I've never actually cast propellant and made my own little rockets to launch, but I think that might be a fun thing to start going into.
How long does it take to build one of those rockets?
For the space shuttle motors, we probably takes about a year before one goes from piece parts all sitting out in different parts of the warehouse and different chemical components all in different bins, and to where you finally start to put it all together, put insulation, put propellant inside, and get it fully integrated and get it down to the Cape. We're probably looking about a year and a half.
Okay. What is the best and the worst thing that has happened to you while you've been building rockets?
One of the best things that's happened to me, obviously the most exciting part is a launch. Get to see the rocket used. That is the best thing by far. It's an awesome experience for just the sound, for the visuals, and just for the knowledge of the effort that was put into it by myself or by the whole shuttle team, getting it ready to fly, and then watching it actually take off and leave Earth's orbit with some of our best friends and good friends inside of the shuttle. That is the best part. Some of the worst parts, and I don't know, I guess it might be worst and best depending on how you look at it. My job does require quite a bit of travel, so I'm gone from home a lot. I do get to go to some pretty nice places. Utah isn't so bad after all. It's really beautiful in the spring. It's great hiking weather and when we're finished with work. But on the other hand, that means I have to be away from my family. So that's the good and bad part, is all the travel that's required.
Okay. What can a middle or high school student do to create a career path towards working in space science at NASA?
Have a desire. That's really all it truly takes. If you want to work in the science field, in the space field, whether it's with NASA or with any other company, you just have to want to do it. Like I was saying earlier, when I went to the Texas A&M, I did my co-op position. I got my co-op job. One of the greatest lessons I learned there was it's somebody else's job to say no. I should never say no to myself. So by calling up Mr. Jewell and asking him for a job, that was a huge difference. Not saying no, because I did try to first say that. I told my brother I can't just call NASA. I told him that also, and he proceeded to get quite angry at me and say that that wasn't my job to say no, that was somebody else's job, and you better call and ask them for a job, or he'll drive 36 hours to come find me and well, just take care of me. So it's a matter of not telling yourself no, letting somebody else do that. Going off and getting a degree in engineering. Obviously, it doesn't matter what engineering field it gets in. If I can do solid rocket motors with a civil engineering degree, if you want to do it, you can do it. But you do have to have an engineering degree or a science degree to go off and pull it off. But it's just that desire of going off and chasing it down and getting there and seeing what you want to do and pursuing it. And don't let somebody tell you no that you can't.
Okay, great advice. What's one of your favorite rocket designs that you've worked on?
Favorite rocket designs. I would have to say I have worked with solid motors. I have worked with liquid engines before for small propulsion systems. And by far, I think I like the solids. There's the simplicity of the design, and a lot of the forethought that goes into what you cast into the solid propellant fully defines how it's going to perform. If you have a large surface area in one area and a smaller surface area in another, you have to really pre-think what you want your solid rocket motor to do before you even come close to casting your propellant and coming up with what you want it to look like. And to me, it's that method of having to figure out the design aspects of what it needs to look like to get what you want is a challenge that I find interesting and I like.
Okay. How many years did you go to college?
Well, I was supposed to be obviously college is supposed to be for 4 years, and I got through my first year of school. I was going to be an aerospace engineer actually at Texas A&M, and I didn't have the grade point average that the aerospace department wanted me to have to continue on with them. So that's when I ended up moving over to civil engineering. Continued to work my grades, actually graduated okay. They adding that transition, that change there, even though it was still within engineering, kind of set me off a little bit for my time phrase. It was going to probably take me about 4.5 years, 5 years to graduate. But then when I started co-oping, because I was gone every other semester working and then going back to school for a semester, it finally did. It took me 6 years from the day I entered school to the day I graduated. It was a 6-year process.
Okay. What would you recommend an advanced college? Would you recommend an advanced college degree for someone who wants to do the kind of work that you do?
Not until you've worked a little bit. And this is, and I'm sure there's plenty of people that would say otherwise, but in my personal opinion, to go off and get your bachelor's degree in engineering, and if you can get a position working with a company, I do that. Go learn a little bit about your field, because what you learn in college, you will apply, but graduating from college is just the beginning. You will continue to take classes, you'll continue to learn, you'll continue your education all the way through your career. I mean, I still take training here every year for at least a week or two weeks a year. I'm doing training and taking classes and learning. So my recommendation is to go off and get in the field, get in the industry, and make sure you know what you want to specialize in if you want to learn something even more so in depth, like you would with a master's degree or a doctorate degree. But get that better understanding of what's going on in your field before you focus early of what you want to do.
What advice would you give to anyone who wants to become an engineer?
If you want to become an engineer, well, like everything else, develop your sense of curiosity. Go off and kind of tinker with things, take things apart, see how things work, make sure you kind of what you want to go in, or start exploring things, whether it's in chemistry or biology or geology or anything of that nature. But start taking advantage of that in your high school days, and go off and explore things, and just find out what you can within the engineering field. Again, it's developing that sense of curiosity, because if you don't have a desire to learn how something works, or try to figure out how something works, that's a lot of what we do as engineers, is we take problems and we solve them, but you have to go in depth into the problem and really figure out what it is. What is the problem that you're trying to solve, so you don't waste your time or effort solving something you don't need to look at.
Okay. Other than solid rocket motors, what other kinds are there, and how do they work? So what other kinds of motors are out there?
Well, it's because other than solid rocket motors, you have solid rocket motors, you have liquid motors. For propulsion systems, ion gas jets, you can have solar propulsion, you can have nuclear propulsion, you can have, there's all different ways of trying to get something to move forward out in space. As you can imagine, in microgravity, where there's no, where it's weightless, which is very different than that, not the fact that there's no momentum required. You have a mass, and it takes some energy to move that mass, get it started moving. Once it's moving, it's going to keep going in that direction nonstop, as Newton has in his laws. So it really doesn't take much propulsion once you're into space. You can have something that just generates 1 pound of thrust and just pulse it, and that 1 pound of thrust pulsed continuously would continue to increase your velocity to where you're going thousands of kilometers per second quite rapidly. So it's a matter of using any one of the different propulsion methods, and depending where you're going, where you're going to be going, how you're going to be doing it, whether you want to even use solar wind to try to propel yourself.
Okay. How much fuel, or what kind of fuel, and how much do you use for every shuttle launch?
Well, on the solid rocket motors, we have 1 million pounds of propellant in each one, so there's about 2 million pounds there. For the liquids, I don't have off the top of my head how much the weight is for the liquid components, the hydrogen and the oxygen. But the whole stack weighs probably about 3 million pounds fully loaded up, and so you have to propel that going up into space. So there's got to be at least more than 3 million pounds of thrust to pick up the whole stack and move it forward into Earth orbit.
Okay. What rocket motors? What happens to the solid rocket motors when they separate from the space shuttle?
Well, that part's actually really kind of neat. If you go to YouTube and look, you can find videos from the solid rocket motor cameras themselves. And what you'll generally see is one booster is looking over at the other booster, and so you'll see the other one just tumbling as they start to come in. But we go through our launch phase, and once we separate off of the space shuttle, the boosters will keep going up into higher orbit and just a higher loft. So they'll keep going upwards until finally they use up all of their kinetic energy and have full potential energy develop, and then they start their long descent down. The descent will it's a process phase. It comes in and they're just kind of re-entering. The videos are really kind of neat because there is a microphone, so you can hear it. It's quite silent at the very beginning. But as you start to re-enter the atmosphere, the air molecules start striking the motors, and they start putting loads on them. They start creaking and groaning and squealing as they come re-entering. Then the parachutes we'll have a drogue chute that comes out, and it'll help to stabilize, and brings out a pilot chute. Will help to stabilize the motor into a vertical fashion. 3 other parachutes will come out to slow the motor down to an acceptable impact speed. And then finally it'll impact into the ocean. When it hits the ocean, air gets trapped inside the motor itself. And so they'll just bob there inside the ocean until the retrieval ships get there. Scuba divers will go inside, and they have a device that they fit inside of the nozzle, and they'll pump all the extra seawater that's collected inside of there, pump it out, pump air inside, drain out the water, and at that point in time now the motors will actually float right on top of the surface of the water. And so the retrieval ships will then tether onto them, and they'll tow them back to Kennedy Space Center. They're on the east coast of Florida. Bring them out. They use the cranes to pick them up. We take them apart, and then we actually ship all of the pieces of the motors back to Ogden, Utah, where we manufacture the motors, and they'll clean them out and then reuse them again.
Okay. Why do you like your job? What parts of your job do you like?
I like the people I get to work with. I like the technical challenges, solving problems there. Most importantly, what I like about working at NASA is, as I've done in my career, you can work on something for a few years, and then if you really want to try to work on something different, you talk with your boss. I've worked three different major areas in my career so far. I've worked 6-8 years in structures at the very beginning, working on the experiments that flew in the back of the space shuttle. I also got to work with microgravity experiments as a systems test engineer, and that was basically as the mother hen for an experiment. I would take an experiment or a facility, and I would take it through all of its testing: thermal testing, acoustics testing, vibration testing, functional testing. We'll go off and train the astronauts how to use our experiment. That's where we'd fly in the KC-135 and the Vomit Comet and train astronauts to use the use of the experiment or the facility. We'd come back, then we'd go down to the Cape. We'd get it integrated into the space shuttle. We'd support launch operations. So I had opportunities to view many launches at that point in time. We'd bring our facility back after the experiment flew on the space shuttle, de-integrate it, bring it back to Marshall Space Flight Center here in Huntsville, Alabama, and then refurbish it. We'd take it apart, clean it all up, and get it ready to fly again. So that one was really kind of neat because it tapped all the different areas of engineering as far as working acoustic loads, structural loads, understanding safety and quality measures that are assured, test engineering, and dealing with all the test aspects of it. So that was a neat thing to be able to delve into all those different areas. And then the third area I worked in again was with the solid rocket motors. And even in the solid rocket motors here for the space shuttle program, I've had the opportunity to work with the nozzles, which are the back end of the motor that direct the hot gases coming out and that provide the thrust for the motors. I've been able to work on the ballistic side, which is the motor performance, how much thrust you get with the pressure, how it builds up and how it tapers off within the motors itself. Mm-hmm. I was able to work in a more mundane area of the engineering side, but just as important to know, I've actually been the head of our business office. So I was handling all of the budget that we have for the solid rocket motors, and being able to handle how we spend that money and where we spend it at, prioritize our engineering tasks, and what we're going to fund and what we're going to push off for the next year. And so that it's not a technical part, but it's a good part to understand and know, to be able to balance out, prioritize what you want to work on and what you're not going to work on. The money part is just as important, I've learned, as the engineering technical side.
What's the hardest part about building a rocket?
The hardest part about building a rocket is making sure that you build it the exact same way every time. When we go to fly the space shuttle, the engineers at Johnson Space Center develop all of our trajectory analyses, and they decide how fast it's going to get in the orbit, what angle, what inclination angle are we going to be entering into Earth's orbit, and they need to know specifically and exactly what is going to be the thrust at what time, and what our thrust trace is what we call it, and what it will look like. So to get a thrust trace that is predictable, that we can tell exactly what it's going to be, we have our design set, and that design was set many years ago, and we build motors the exact same way every single time. And if you have a change in your process or a change in your manufacturing methods, that's essentially a change in the design. It'll affect how the motor performs. So the most difficult part is building it the same way every single time.
Okay. And as a follow-up to that, what's the easiest part of building a rocket?
The easiest part of building a rocket, shipping it. Because we put it on the rail cars and we'll ship it down to Kennedy Space Center by train. That really is probably the easiest part. Everything else, there's so many things to be monitoring and controlling. It's a challenge. It takes a lot of people to monitor and observe that and make sure that it's built the same way and that it's safe.
When you flew on the Weightless Wonder, tell us about the experiment that you were flying.
The experiment. It was a microgravity glove box. So essentially it was, and actually there are some teacher things out there that we have, some teacher
plans
to be able to use and work with glove boxes and how they might work. But essentially what it is, it's a metal box with plexiglass, clear plexiglass on top, so you can, the person who's running the experiment, the astronaut or the scientist, would be able to put the experiment inside of this enclosed box. They would put the doors back on it, and the doors on each side have rubber gloves in them. And so you stick your hands through the rubber gloves, and then you can manipulate the experiment inside of the box and not have to worry about any contaminants or anything hazardous coming out of the box. For example, we would do combustion experiments, and when you burn something, you make carbon monoxide, and carbon monoxide is a bad gas to breathe, obviously. We'd also do biological experiments inside. We'd handle experiments that have liquid chemicals that would be caustic or dangerous if they were to float in microgravity. And you have to remember, it's very different in microgravity, because if something were to escape out of your experiment, in this case, if it wasn't being done in a glove box, if you had a liquid that might be toxic or something that would be somewhat acidic, and even if it was something like vinegar, obviously it wouldn't be comfortable getting vinegar in your eye. And when you're thinking about that in microgravity, once it gets out, everything will go to its natural shape. And for liquids, with surface tension, they all love each other. These molecules are always pulling in, and so the natural shape for a liquid is a ball. And so a lot of times you'll see experiments with the astronauts, if they pop a water balloon, the rubber will disappear, and you're left with just a sphere of water. And at first it's kind of a pretty big mess, but it'll slowly come back together with the surface tension pulling it. So if you have that floating around, especially if it's small molecules or small bits, droplets of substance, it's very easy that it could get into your eye. So that's why, again, we do things inside of this glove box. And that was the facility that we had when we were flying on the KC-135. We would mount the glove box on the floor, because the box that handles all of the air flowing, air control, was bigger than the compartment that we put the experiment inside of. So if you mounted it on the floor of the airplane, I had enough room that if I sit cross-legged, my legs would fit underneath the area where you'd be running the experiments, and so you could be right on top and looking down into the glove box with your hands inside the gloves. They'd also give you a Velcro strap that was on the floor, and we'd take the strap and I'd put it over my lap to help hold you down. But again, it's a very weird sensation, because you're sitting on a chair like Christy and I are now. We're sitting in chairs, and we have this sensation of pressure on our bottom, and that's very natural, comfortable. That's what you expect when you sit down. Mm-hmm. When I first hit microgravity going into a parabola, you start to float, and that pressure is gone, and it does not feel right. In fact, the sensation was that I was tumbling over. I was about to pitch over forward, even though I mentally and visually I could see that I wasn't moving, but your brain convinces yourself that you're moving. So my first reaction was to grab the bottom of the facility and pull up as hard as I could to get that pressure back on my bottom. And so that's why I failed to do any science on my first parabola, because I'm struggling just trying to get that pressure down, and it was very nerve-wracking. So finally, on the second parabola, I just relaxed and enjoyed the flight, and after that it was quite easy once you get used to the sensation of losing that pressure on your bottom. But I guess back to the question, it was the glove box, and we were flying with those and running those experiments.
Okay. Well, what will you be doing once the shuttle program ends? You had talked about the Centennial process, the Centennial program.
The Centennial Challenges. So hopefully I'll be finding bright people, great engineers that are just maybe not even in the engineering field, that are trying to solve and want to help solve our problems, and hopefully try to give them large amounts of money for prize money to be able to solve these things. One of our challenges we had recently was astronaut glove. And so we had Peter Homer was the actual winner that received our initial prize money, our first level prize money. He went off and was literally working in his garage, had a sewing machine, and decided he thought he could build a glove. And so he built an astronaut glove, and actually turned out to be the best contender that we had. He didn't have any intentions really of knowing what he was going to do afterwards, but from that competition win, actually went off to start a company building space hardware and not space hardware, but space suits that people could wear. He's now a vendor for the NASA, for the shuttle, not for the shuttle program, but for NASA for other space suits that we're going to be developing. And he's also been a vendor selectee for some of the private companies out there that are going to be needing space suits here in the near future as they fly people in orbit.
Wow, that's great. How do you test the motors for errors that they may have in them?
We do testing at all different levels. We'll do some motors that are no more than 5 inches in diameter. So we'll have our 5-inch center perforated motors that we'll test to tell us what the propellant characteristics are, how fast it burns, how fast it burns, how quickly, how much thrust it'll be able to develop. We'll also do motors that are maybe 24 inches in diameter. We'll do motors that are 48 inches in diameter. We'll do propellant, just what we call milk carton testing. We have like milk carton bricks of propellant. We'll burn that. And then finally we get up to where we're comfortable with understanding if we did have to make a design change because either a vendor went out of business or they quit manufacturing components that we use for the solid rocket motors. we'll need to test that before we fly it and put people in on that motor. And so we'll do that with all of these subscale tests first, and then finally we'll go ahead and integrate it into a full-scale solid rocket motor. And so about once a year, we'd always take one of our solid rocket motors and we put all of our changes on it that we have experienced in the prior years that we're trying to get certified so we can use to build future motors to fly. And then we'll finally burn one of those solid rocket motors sitting on its side. So we'll be up there north of the Great Salt Lake. They have a large test facility, and they'll just have the solid rocket motor sitting on its side with the nozzle pointed towards the mountainside. And we'll have a cage at the very front of the motor that'll, when a motor is burning, it'll push against that cage, and we'll be able to measure the thrust off of that. So we'll do a full-scale motor burn is how we'll go off and test all of our design changes. That too, it's all for burns for 2 minutes. It's quite loud, it's quite bright, as the solid rocket motors are with burning the aluminum. And just take all of our test measurements from that, look at our data afterwards. If we had motor performance as expected, then we'll go ahead and we'll use that. All those design changes were there, they'll be accepted as proven and acceptable for flight, and then we'll incorporate that in our design cycles as we start building more motors to fly out in the future.
Okay. Why do we launch rockets from the west coast of the United States at the Air Force Base in California?
Well, why do we not, or why do we?
Why
It
are they
depends.
launched
Okay.
from that area?
So it depends on what you want to do or where you want to go. If we're going to orbit the Earth around the equator, in an equatorial type orbit, you're going to launch from the East Coast. You'll launch from Kennedy Space Center there in Florida, simply because the Earth is already turning as the sun moves, and you're launching in the same direction that the Earth is turning. So you take advantage of the rotation of the Earth to get extra speed to be able to launch yourself. Okay. On the West Coast, the reason you can do it from there is when you want to go into a polar orbit. That's when you want to go launch directly north, and you want to go around the poles. And so when you do it that way, on the West Coast, you're going to be launching out over the ocean in that direction. Instead of from on the East Coast, you'll be launching back over the land. And so you want to make sure that if you do have a problem, if you do have a failure of your vehicle or your launch systems, it'll just splash harmlessly down into the water.
Okay. Do your children have an interest in what you do, or want to do that in the future?
Yes and no. I have my daughter is 16 years old and my son is 14 years old, so they are old enough to have interests and desires and what's kind of neat. They are both, I think, very highly fascinated with what I do. They think space exploration is totally cool. They think the shuttle is really neat. They've been fortunate enough to be able to go down to Florida and see a shuttle launch, and are very excited about that and watching those kinds of things and hearing stories about what goes on at my work. Although my daughter is an accomplished classical ballet dancer, so in her mind, that's all really neat stuff, but she wants to dance professionally with a company. So it's neat, but for her, no, that doesn't want to touch it. My son, on the other hand, I think he does have an interest and has a desire to figure out how things work, take things apart, and has that curiosity, and has expressed an interest possibly in going into the engineering field, whether it's actually into aerospace engineering or space exploration. I don't know. I mean, there's plenty of time still for him to decide what kind of field he wants to get into.
How much of your job deals with math, and how much of it is science?
I guess I'd make it difficult, because I consider math and science to be somewhat the same. They're very closely tied together. They are very tied. And quite a bit of it. To do any of these calculations for our motor performance, for what our specific impulse measurements were, what's our thrust, what's our surface area that we have that's burning at any given time with the motor, because it changes over time. That's all math related. The science side is the chemistry side of the experiment, of the propellant that's mixed into it. The chemistry side, if you have liquid engines, of the fuel mixture ratio of the hydrogen and oxygen, or the isopropyl alcohol and the oxygen. There's science involved in all of that. So it's all really intertwined together. Right now, and if the question was related to the science of experiments or things that we're trying to explore, whether it's genomic or protein crystals or biological type experiments in science, that part is very separate from the solid rocket motor world. We are a school bus providing transportation. So we get people up into space. We transport the experiments. We transport things on the solid rocket motors to get the scientists and science experiments up there. So that part would be very different. But as far as within the world of propulsion, it's very closely tied together.
How many parts are there of a solid rocket booster?
Hundreds and hundreds and hundreds of thousands. But when you start putting them together, there's really probably about 4 or 5 major components. There's 4, 5, 6, 8 or 10 major components. There's 4 round cylinders that we call case segments, and so we'll stack the 4 cylinders together, and that makes the significant part of the motor. In the aft end, you'll put in the nozzle, which is a cone-shaped structure that allows us to develop the propulsion and thrust forces from the hot gases that are coming out. What we call the booster part of it, which would be added onto the motor to make it a complete solid rocket booster, they have what's called the aft skirt, and that gets put onto the back end of the motor, and it has the actuators and energy systems inside of it to be able to steer the motor. So it pushes the nozzle one way or the other to help steer it. On the forward part, you'll have a nose cone, and the parachutes are all up inside of that area. So you have that attached onto the front of the motor to finish out the whole solid rocket booster.
Okay. How many people work on the solid rocket motor boosters?
I guess probably within about the last 5 years, because we've finished building all of the motors we need to fly out the Space Shuttle program with our last 2 launches coming up here soon. But up to maybe about 5 years ago, when we were in the height of really building motors and getting things ready for a continual flight process, we probably had on the order of between the contractors supporting us as well as the NASA people supporting it within the solid rocket motor side, it might have been 1,500, 2,000 people total.
Okay. If you weren't a civil engineer with NASA, what do you think you would be doing?
Wow, if I wasn't an engineer for NASA, I always joke around with my kids, I'd be a cowboy. But yeah, I think my curiosity is still there. I would still be going off and working somewhere in an engineering field. Even if it wasn't with NASA, if it was with a private company, I would still be taking things apart and building things.
Okay. What innovative products are going on with NASA and contractors?
Innovative products. We're really digging out, and my definition of innovation is coming up with a unique way of solving a problem in a more simple fashion. So that's how I'll define innovation. And the innovative things that are going on, we're going off and working with companies to come up with easier solutions to things that we need. One of the things is for researchers wanting to do research in microgravity. But there's an area that we call the ignorosphere, because we have weather balloons that will go only so high, maybe up to about, let's say 80 kilometers. Earth is space is defined at 100 kilometers, so that 80 to 100 kilometer range, we really don't have much that can get into that area and be there for a very long period of time. Sounding rockets will go through it, but they don't stay there for any length of time. Mm-hmm. So that area of the atmosphere that we would like to study, we're going off and trying to find companies, and we have 2 companies right now, Armadillo Aerospace and Maston Space Systems, that are developing rockets that will go to suborbital, so they'll get right up to that 100-kilometer range, but they won't go into orbital around the Earth. And they'll be able to fly and coast through that zone area and be able to do microgravity experiments and have periods of microgravity up in the minutes, as opposed to just 40 seconds like we have in the KC-135. And we'll be able to do those science experiments in there. So there's some innovation going on between them. There's more innovation going on between trying to find vehicles that are low cost, low complexity, that we'll be able to use to land on the moon if we decide to go back and land there. So we have propulsion systems that can get mass up into Earth orbit and up to a translunar transfer stage. But what we'd really like to do is try to find cheaper, more economical, lower weight versions of lunar landers. And so we have innovation going on there that we're partnering out with private companies as well, trying to come up with solutions for that. Other innovations we have going on, the first A of NASA is aeronautics, and that's airplanes. And so there is some innovation going on trying to reduce noise, trying to reduce the amount of fuel consumption for an aircraft. Like I said earlier, the Green Flight Challenge, where a regular airplane right now would take 9 gallons to go 200 miles. The innovation there is trying to come up with aircrafts that will take 1 gallon or less than a gallon to be able to go those 200 miles. And so there's a lot of innovation aspects going on there.
Have you ever worked with model rocketry?
I have. My son and I, and my daughter too, we've been launching Estes rockets, gosh, for 10 years now. So it's fun. It's kind of neat to work out. We've gotten to the level of where we have little payloads coming off of our rockets, but we never have had a dual stage rocket. So that might be the next thing to start venturing into, is being able to launch one and then launch another one from off of that one as well.
Okay. What size rockets do you use?
We're still at the A, B, and C range motors to get the beginner level. We're at the beginner level. Yeah.
Well, good. Is it true that the solid rocket booster's size is dependent on the width of train tunnels?
You know, I have seen that email going around generated that actually goes all the way back to the Roman Empire, right? With the ruts of the chariot wheels.
Right.
I don't know. I'll have to just plead, I don't know. But obviously, by the tunnels, did we design it to do that? Yeah, because we couldn't design it any larger than that. So that was one of the constraining design elements that's there. And that goes into anything that you newly fabricate, you newly build. When you're doing it, there's not only design constraints of the tunnels, of transporting it to the final use site, it's also the facilities that we had at Kennedy Space Center were built originally for the Apollo days. And you really can't, these structures are huge structures. It would take a lot of money, a lot of time, a lot of effort, and when you could have just designed your vehicle to fit what you already had. So there's a lot of constraints that were given to us as we started the shuttle program that we had to fit into, and just kind of slowly made our design evolve to where it did that. So see, I guess, did the tunnels contribute? Yeah, they probably did.
All right. What is a jado tube?
A jado tube.
Do you know what that is?
No, I'll have to plead ignorance on that for now. But I will go look that up and see.
Okay. How will NASA get things to and from space once the shuttles have retired?
Well, you know, the retiring of the shuttle program isn't a big shock or surprise. That was declared back in 2003. So it's for 7 years now. We've known that we were going to be retiring our space shuttle program, and preparing for that. So the question being that how are things going to get to and from space is we've already delivered everything that's large that we need to get up into space. And the purpose for maintaining the shuttle program this long was to finish out the fabrication and complete the build of the space station itself. So we've delivered all of the significant major components. These last few flights are going to be putting extra supplies, extra experiments, larger racks of experiments up into the space station. And then once we have everything up in there, it's just a matter of swapping out the smaller experiments, and that we can do with our supply ships that come from either Japan or from Russia, as well as the Soyuz launch rockets that come from Russia, is how we swap out crew to be going up there. We have done contracts out to other vendors within the United States. We have SpaceX Corporation, which has a vehicle that they've been launched a few times now, and there are a prime contract that's out there for trying to get them to be the point where we would use that service as well as other international partners to be able to put people up into space and get our astronauts swapped out as well as crew and experiments.
Okay. How do you know when the rocket boosters have to separate from the space shuttle?
Those are defined, again, by design. They're built to fire for only 120 seconds for 2 minutes. We have pressure sensors that measure the pressure within the combustion chamber of the solid rocket motors itself. And once they reach a certain value, it'll trigger the mechanism for how we start to do our separation process. And that's when we have booster separation motors. There's independent motors that are mounted at the nose of the space solid rocket boosters and down to the tail end. and those are the motors that will drive the boosters away from the whole stack as they pull off and they start to tumble down into reentry.
Okay. Did you always know you wanted to work for NASA? You mentioned this a little bit earlier. That
I did, and no. In fact, I'm not a kid that knew it when I was 6 years old and watching the Apollo stuff. In fact, I don't even remember Apollo. I mean, bad as it may be. I really didn't even know NASA existed. In fact, until I was a junior in college, I really didn't even know where Huntsville, Alabama was, much less that NASA had a center there. It wasn't until I stumbled onto it through discussions with my brother, getting my job and going off to start co-oping and working here part-time. And then it was just an eye-opening experience, a whole new world, and discovering all that we did. I'm hooked on it. I love working for NASA, and I don't really see any reason why I would go work anywhere else right now.
What kind of goals do you have as you continue your career?
That's actually a really good question, because that's what establishes who you're going to be 5 years from now, 10 years from now. So even a lot of the students here in high school, or the students that are in college, you need to have your goals set to know what you want to do. How do you get to where you want to be? For myself, my goals are to continue learning more about anything in the aerospace field and outside of the aerospace field. That's really what I've focused on for the last 25 years, is just the space shuttle, experiments, space structures. I'm really excited about this Centennial Challenges job, because I'm really starting to learn more about what all else is out there, whether it's with aeronautics, whether it's with robots and lunar rovers and Mars rovers, whether it's with vertical takeoff and landing vehicles, all different areas and aspects, all the different science platforms that we have at NASA. It looks like I'll be able to get to work with the Centennial Challenges. So that's kind of fulfilling my goal of becoming a more classical engineer, of working in all different areas.
Okay. What kinds of things do you like to do in your off time when you're not at work? What kinds of things do you?
Activities with my kids. That's the biggest thing. I'm assistant coach for a soccer team. I'm an assistant scoutmaster for a Boy Scout troop. So we do a lot of camping, a lot of hiking, do a lot of running around and kicking the ball around and just playing and having a good time. And that's probably the biggest thing, is just playing. In my off time, I like to play.
What's been one of the most significant launches for you personally, and why?
The most significant one was probably our return to flight after the Columbia accident. I was at NASA headquarters for a year, just for developmental training and learning how NASA works as an agency level. I had just gotten there in November, and then the Columbia accident happened there on February 1st in 2003. At headquarters, I got to see our contingency action plan kind of develop into place, and after the first 2 weeks, the head NASA director of recovery operations was swapped out with another person just to help keep him from burning out. The person that replaced him, Mike Rudolphi, called me up and asked me if I would come and be his executive officer for recovery operations. So I had an opportunity to interact with a lot of different agencies, a lot of great people from FEMA, from the Forest Service, from the Texas Forest Service, from the EPA, and just helping us to recover a lot of our pieces and parts that had fallen all over the state of Texas, to figure out what happened, how did it happen, and how do we recover from that and change our design so we can fly safely again. So I did lose a good friend there in that shuttle launch. So to see us recover and get back into a flying mode, I would say it was that first flight after 107.
Besides Marshall, what's your favorite NASA center, and is there one that you would recommend visiting, or one of the visitor centers that you really like?
Yeah, I guess that's kind of hard to say, because every center has its own specialty or its own knowledge base. Obviously, here at Marshall, we do space structures and space propulsion. Kennedy Space Center is a neat one because of its launching. Johnson Space Center because of their astronaut aspects and the training and controlling of the vehicles that we launch. Langley, with all of its research that they do for aeronautics, and Ames for all of its research that it does with robotics, and then Glenn Research Center, they do a lot of science and propulsion as well, a lot of jet engine aircraft propulsion. So at Dryden, we do a lot of our flight testing, and everything is just so neat. I'd be hard pressed to say which one's my favorite one. Everybody has some neat stuff and neat, very interesting things to me for that. As far as visiting, for the most part, all of them have a science center or an outreach center that you can go to. Especially, I know for a fact, Johnson, Kennedy, Marshall, we have our space and rocket centers that are associated with the space center itself, and they have a really great exhibit area to be able to go see space artifacts and learn more about science and space. So, those three would be kind of, if you're ever in those areas, if you're ever down in Texas or Florida or here in Alabama, I'd recommend going to the space and rocket centers there and visiting and seeing what they have.
Okay. And this will be our last question. Does a solid rocket booster ignite from the top down, or from the bottom to the top, or the top to the bottom?
Neither.
How does it? Neither.
Those would be called end burners, where it would consume the fuel coming up or consume the fuel going down. What we have within the solid rocket motors for the space shuttle is just a cylinder, and there's a hole right through the middle of the propellant, and the igniter up at the top of the motor will shoot a 40-foot long flame down that hole and lights the whole interior, and so it burns out this way to the walls of the metal walls of the cases.
Okay.
So it's a center perforated motor, and it just burns to the outside.
Neat.
Yep.
Well, that was our last question. Our time is up. Thank you for joining us today, and thanks for Sam for joining us today.
Thank you. It was
Enjoyed
great.
having you. Join us next month, and see you later.
Have a good
Goodbye.
day.